Welcome to lecture number 29 for ECE 476, Advanced Embedded Systems, PIO State Machines. Now, the programmable input-output state machines are semi-unique features of the Raspberry Pi Pico. These are independent processors which are able to drive the I/O pins. These are described on page 34 of the Pi Pico datasheets. You'll link up here. In there it states the PIO subsystem on the Raspberry Pi series microcontrollers allow you to write small, simple programs for what are called PIO state machines, of which the Raspberry Pi 2040 has 8, split across 2 PIO instances. So that means is the Raspberry Pi Pico's got 8 microcontrollers in addition to the Raspberry Pi Pico, and those are designed specifically for I/O functions. The intent is to make non-standard communication more efficient. So I'm not tying up the processor for bit banging. I can have all these separate PIO state machines handle the bit banging. Examples would be like the NeoPixels, the HT11, HT22 temperature humidity sensors, or pretty much anything else that has a non-standard interface, something other than SPI, I2C, and UART. And where we're heading in this lecture is I want to be able to control the NeoPixels, an example of a non-standard I/O device, without tying up the microprocessor using bit banging. Now for the state machines, there are 4 state machines available. Each can run a short program that's limited to 32 instructions with a reduced assembler instruction set. The clock range of each of the state machines is anywhere between 2 kHz and 125 MHz. And each state machine can read from the I/O pins, they can write to the I/O pins, and pass data to and from the Pi Pico via first-in, first-out buffer. The instructions available for the state machines is a reduced set of assembly instructions. I can do in, that'll shift 1 word of 32 bits into the input shift register. Out shifts 1 word of 32 bits from the output shift register to other locations. I can do push, that sends data to the transmit input buffer. Pull gets data from the transmit buffer. Move moves data from one location to another. IRQ sets or clears an interrupt flag. Set writes data to a destination. Wait pauses. And jump is the jump command. And that doesn't seem like a lot, but it's enough to program some fairly elaborate I/O functions like CAN buses, driving NeoPixels, reading HT11 sensors, and so on. The topic for this lecture, we're going to look at how to generate a 1 kHz square wave using the PIO functions. That's the basic program. Modify it to add wait states to output a 1 Hz square wave, basically looking at looping. Output a 2 kHz square wave with a variable duty cycle. That allows you to do illustrating multiple PIO functions. One sets, one clears. I'm going to generate a pulse with n bounces, so I can basically pass data to the PIO function, tell it how many bounces I want. And finally, drive a NeoPixel. I'm going to generate a non-standard output with precise timing. So that's where we're heading. Starting out, let's output a 1 kHz square wave. This is the basic function of a PIO state machine. What I'm going to do is import time, Raspberry Pi 2, and from machine import pin. I'll define a subroutine blink. That's just going to set a pin for 1 clock. Well, set a pin, clear a pin, and wrap. Wrap means repeat. Now here's how you define the PIO state machine. This is using RP2. I'm going to define a PIO state machine. The initialization, I'll initialize it to low, and then the state machine will be subroutine state machine. When it's called, it's going to call subroutine blink. The clock of the state machine is 2 kHz. And the state machines are separate processors. You can set their own clock frequency. And the pin that I'm using is pin 16. Now in the main routine, I'm going to activate the state machine for 3 seconds, then deactivate it. So here's what that looks like. If I go over to Thonny and run this puppy dog, I see a square wave on the oscilloscope for 3 seconds. Running again, there's 3 seconds, turns on. You can also see the LED turning on the Pi Pico. If I expand that, I'm going to run it. There's a 1 kHz square wave for 3 seconds. Now explaining the program, the way that works, this is the subroutine that's called at 2 kHz. What this does is it sets a pin, clears the pin, repeats. Each instruction is at 2 kHz, so this is 0.5 milliseconds, 0.5 milliseconds, repeat. So this is 1 millisecond period, 1 kHz. Setting up the PIO State Machine. This is PIO State Machine number 0. There's 4 of them you can choose from. The state machine is running at 2 kHz. I could go all the way up to 125 megahertz. 2 kHz is the lowest you can go. The pin that I'm using is pin 16, and the subroutine is called blink. Now when you initialize the state machine, you can also specify input pins, input shift direction, output shift direction, other parameters. Those are explained in more detail in the manual and a little bit later up in this lecture. The last set of comments turns on the state machine for 3 seconds, then turns it off. The net result is a 1 kHz square wave. And you can play around with it. Let's go back over here. If I change this to, let's say, 4 kHz, put that up on the side so you can see it. At 4 kHz, it is now 2 kHz output. Again, it's 4 kHz clock frequency. I need to set and clear. I change this to 10 kHz. It's now 5 kHz. This doesn't tie up the main processor. That's all done in the hardware. So that's the advantage of it. I'm not tying up the processor with I/O. Okay, so that's the base code. If I want to slow it down, one option is to add wait states. If I do 31, what 31 does is that's basically 31 no-ops. It pauses 31 clocks after each instruction. I can also add a no-op. What this does is I'm going to set bit 1, wait 31 clocks, clear, or do nothing, wait 31 clocks, set, wait 31, clear, do nothing 31, repeat. The biggest you can do is 31. It's just kind of a feature of the state machines. I can only have 32 instructions. I can only have 32 pauses. If I do this, what I get is a 64 millisecond square wave. Again, 31 no-ops, where each loop has 4 instructions, plus there are 31 times 4 no-op instructions for a total period of 64 milliseconds. That shows up here. The period is 64 milliseconds. If I want to do 1 Hz square wave, I need to start doing some looping. So this is getting a little bit more fancy. If I want to do 1 Hz, what I'm going to do is set pin 1. I'm going to move 10 to register X. That's what the set X, 10 does. I'm going to have a label. That label's for my looping. I'm going to move 10 to Y. Have another label. I'm going to do a no-op for 6 clocks. Plus 1 for the no-op makes it 7 clocks. So this right here is 7 clocks. I will then check. I'll decrement Y and then jump to loop 1 if not 0. So it's going to keep on looping until I get to 0. Once I get to 0, I'll decrement X, jump to loop 0 if not 0. So there's my looping. So it's going to be 10 times 10 times 7. Then clear a pin, repeat. What that does is the loop time, this actually loops 100 times. 10 times 10, keep looping. Each loop takes 10 clocks. That's 7 clocks for the no-op delay, plus 3 clocks for the jump instructions in the label, for a total of 1,000 clocks. If I try that, I get 1 Hertz. So here's the blink 1 Hertz program. As I run it, you can see the lights turning on and off at a frequency of 1 Hertz. Okay, so that's some things you can do. For aliasing, I can actually have 2 PIO state machines running at the same time, and they could be running at different frequencies. For example, if I have the first state machine always turns off an LED at 2 kilohertz, the other one always turns it on at 2001 hertz, I get a 1 hertz beat frequency. They're slightly different frequency, causing the pulse width to vary in width. What the code does is I'm going to initialize 2 PIO state machines. The first one turns on the LED. The first one turns it off. The second turns it on. I'm going to turn off at 2 kilohertz, turn on at 2001 hertz, both using the same pin, pin 16. And here's what that looks like. I can see the LED varying in brightness. I can see the pulse width varying. The period is 1 second. That's your beat frequency. The difference in period is 1 hertz. If I switch to 2000-2001, I get bright and then dim. So that just kind of illustrates that you can actually have 2 state machines running at the same time. Their clocks don't have to be the same. Next example. Let's just have it blink n times. I can pass data to PIO state machines with the put instruction. So PIO programs can be triggered by the main routine. They're triggered whenever data is pushed onto the stack. That also allows you to pass data to the PIO state machine. For example, let's have it blink n times. Each pulse is going to be 1 millisecond on, 1 millisecond off. So if I execute put 3, I get 4 pulses. The code that does that is as follows. I'm going to turn on a PIO state machine. I'm going to have PIO state machine 0, calling subroutine blink n at 2 kilohertz on pin 16. When I put the number 3 onto the stack, that triggers the PIO state machine. It's going to pull the number off the stack, move that into X. Keep on looping as long as X isn't 0. Well, if X is 0, I'm going to jump to the end. Otherwise, I keep looping. On this label, I'm going to set pin 1, wait a clock, clear the pin, or set the pin 16, wait 1 clock, clear the pin, another instruction, that's 2 clocks, then repeat. If I push the number 3 onto it, I'm going to get 4 pulses. So trying that, let's go to blink n. There's the pulses. Yeah, it looks like I modified the code. Added this line, so if X is 0, I jump to the end. So this way, when I pass the number 3, I get 3 pulses. So there's your 3 pulses, and the width is 1 millisecond. So let's try that. Let's send 4 pulses. We've got 4 pulses coming in. So we can pass data from the main routine. every time I pass data, every 0.5 seconds, I trigger the PIO state machine. You can pass data to it. Okay, so here's something that's kind of useful. Bouncing is a feature of mechanical switches. The problem with bouncing, one of the problems with debugging bouncing, is it's kind of hard to consistently generate a bounce signal. So let's do that in software. What I want to do is every time I set, I want to have it bounce a fixed number of times, then go high. That way, I've got a controlled number of bounces. I can come up with my debouncing techniques, hardware, software, whatever you want, and see if I can fix the bouncing. So to do that, I'm going to use two PIO state machines. The first one is going to set GP16 after n+1 bounces, and the second one clears GP16. The calling sequence for 6 bounces is put 5, then put 1. And what the code's going to look like is for the first state machine 1 is pretty simple. I'm going to pull data off the stack. I don't really care what the data is. I'm just going to clear the pin. State machine 0 is a little bit trickier. I want to generate n bounces. So what that's going to do is I'm going to call it by pushing 5 onto the stack. I will move the data into X, have my label. I'm going to set, wait a clock, so that's 2 clocks, clear, decrement X. If it's not 0, keep looping. When it is 0, I'll then set. So here's the overall code. I'm going to have 2 state machines. The first one is to set a pin. The second one clears the pin. Well, this one actually toggles it n times. This one always clears it. This is always set when you're done. It's going to do like a bunch of bounces, then set. Later on, I'll then clear the pin. There's my bouncing on the inputs. I'll define 2 state machines. State machine 0 is at 10 kilohertz using pin 16, calling subroutine set pin. State machine 1, call subroutine clear pin, also running at 10 kilohertz using pin 16. Activate the 2. I'm going to then set a pin with 5 bounces, wait 10 milliseconds, then clear it. So I should have a 10 millisecond pulse with 5 bounces. So trying that, let's run this puppy. If I zoom in on it, kind of hard to see. 1, 2, 3, 4, 5, 6. 6 bounces, then it goes high. If I slow it down, you can see the bouncing. There's my pulse. It's 20 milliseconds per division, 2, 4, 6, 8, 10. 100 milliseconds. That's what this is doing here. The thing to note is the state machines are running in the background. This doesn't eat up time, unlike bit banging. This is done by hardware. Once I call it, it comes back to the main routine. The hardware is taking over all the bouncing. For example, let's do 50 bounces. It's still 100 milliseconds. If I zoom in on it, another way, I've got 50 bounces on here. I can pass data to it, have a couple subroutines, and I can have a fixed number of bounces. So let's do like 2 bounces. I need to get triggering. I'm not sure how to get triggering on this oscilloscope. So there's 3. And that's what she looks like. I get n+1 bounces, or 6 bounces in this case, and the total width is, in this case, 10 milliseconds. The demo over here was 100 milliseconds. The last thing to look at are neopixels. So neopixels are non-standard I/O devices. Logic 1 and logic 0 are defined by pulse widths. Each bit is 1.2 microseconds plus minus 120 nanoseconds. Logic 1 is a 700 millisecond pulse plus minus 120 nanoseconds. Logic 0 is 300 nanoseconds plus minus 120. I'd like to generate that waveform without tying up the CPU using bit banging, meaning using the PIO state machines. That's really what the PIO state machines are really designed for. The first step is I want to send green, red, blue data to the PIO pins. I'm going to do that by sending a single message that's 24 bits. The PIO state machines actually use 32-bit numbers, so I'm going to send a 24-bit number that's left justified. So it's going to have 32 bits, 4 bytes. This one's green, this one's red, this one's blue. That's not used. So to do that, I'll specify the color, green, red, blue, shift them into the shift register, or shift them into a 32-bit number, shift it 8 times, gives you these fields. And then this is the state machine put that puts this number onto the stack. Inside the state machine, every time I do that, that's going to trigger the state machine. I'll pull that number out of the stack. I'll store the number 23 into X. That's basically shipped out 24 bits. I will move the most significant bit of the output shift register to Y. Then shift left. As I shift, I'm going to output a 1 or a 0. 1 is 700 milliseconds high, which is 500 milliseconds low. This is running at 20 megahertz, so 700 milliseconds is actually 14 clocks. So here's 1 plus 13 gives you 14 clocks. It's 1 for 14 clocks. 0 for 10 clocks. 500 milliseconds, that's on a 1. For a 0, it is 300 milliseconds, 900 milliseconds. So here is 6 clocks, 18 clocks, 1s and 0s. I'll then repeat, shift the data 24 times, setting bit by bit. Then the calling routine is I'm going to call state machine number 0. The subroutine is my NeoPixel program at 20 megahertz on pin 12. Let's see that operate. If I output 000, the NeoPixel turns off. You kind of see that over here. If I output FF00, I get a green light. Here's red. And here's blue. And this is working on the NeoPixel on your board. The timing is correct. This is the 300, 700 nanosecond for 1s and 0s. And I can do other combinations. Let's do pink. So that's red. Let's try 100. 50-50. That should give me a pink light. So there's pink. Or yellow. Let's do orange. There's orange light. If I look at the timing, I can see the 1s and 0s. So here's a 0, here's a 1, 0, 1, 0, 1. Here, this is where green is 5, 5. So I can see the bit pattern. 5 is 0, 1, 0, 1, 0, 1, 0, 1. I've got the timing correct. Okay, that's talking to a single NeoPixel. If I want to talk to n NeoPixels, I can be a little bit fancier. I'm going to send all the data onto the stack, go to the state machine. When I do that, I will trigger the PIO state machine, But starting out, I'm going to send a whole bunch of data on the stack. So let's do 16 neopixels. In the main loop, I'm going to go through all 16 neopixels, set the green, red, blue brightness, express that as a 24-bit number, push that onto the stack for the PIO state machine, do that 16 times, wait 50 milliseconds. That's going to trigger the neopixels to accept the data and display it. Inside the state machine, I am going to pull off the first number is the number of pixels. So when I start out, I'm going to write the number of pixels on the state machine. That's n-1, 16. Pulls that off. That's how many times I have to loop through this, how many neopixels I have. For each neopixel, repeat logic 1, logic 0, doing that 23 times, 24 times, repeating 16 times, with the result being I can drive all 16 neopixels. Okay, so let's see how that works. Here I've got the main routine is just kind of shifting the green, red, blue. Every time I go around, every time I loop, the index x increases, which kind of shifts everybody around. On the display, you can see the colors moving around. And this guy right here is pixel 0 on the board. And the other 16 neopixels going around. This doesn't tie up the processor. Again, the PIO state machine is handling all the I/O. It's driving the 16 neopixels with the correct timing. All the main routine has to do is just put the data on the stack, and it's done. That's kind of the idea behind the PIO state machines. I have a device with a non-standard interface, namely a neopixel. I could drive that using bit banging if I wanted. With the state machines, I can do that without bit banging. The state machine actually does all the bit banging for me. So, in summary, PIO state machines are a fairly unique feature of Raspberry Pis. With state machines, you're able to drive devices which use a non-standard interface without having to resort to bit banging. And while driving the device, the main routine is free to do other stuff. That allows you to improve the efficiency of coding with the Raspberry Pi Pico. So that's lecture number 29, kind of an introduction to the PIO state machines.